Now let us study about collisions. Okay, we know collisions happen when two objects hit each other. So this happens in everyday life. Okay, let's see some examples there. Commonly we have played carom board. Okay, in carom board a striker will go and hit a coin. There's a collision there. Okay, next is billiards. Okay, in billiards what happens is two balls will hit each other. Okay, and then it goes to the pocket. Then next one is we have the marbles there. Okay, some of the students will play with the marble there. So one marble will go hit the next one. So that's a collision here. We have many examples of collisions. Okay, let me write the example here. So example, that is first one we saw, that is carom board. Okay, carom, the game of carom. Then next we saw that is billiards, and then marbles, and so many of the examples are there. Okay, there are a lot of examples. So in collisions, okay, we see that two objects hit each other. Say for example, in air, the nitrogen molecules may hit each other. Nitrogen may go hit an oxygen atom, okay, or molecule. So this happens. Sometimes collisions may happen without physical contact also. Let's see that now how it is possible. So collisions without physical contact. Collision may happen without a physical contact also, without even touching. Okay, without physical contact. Okay. So for this, we must see an example of a spacecraft called as Voyager 1. Okay, so Voyager 1 spacecraft was launched from Earth in the 1970s. Okay, so let's imagine this thing is Saturn, okay, or Jupiter or Saturn. It first went to Saturn. It must go to next planet. Okay, it doesn't have the energy to go directly to the next planet. That is, say, Uranus. Okay, so what does it do? It will go around the Saturn. Okay, the spacecraft goes around Saturn, and then it will orbit it. Then it will fly to Uranus here. Okay, so while going around Saturn, okay, the spacecraft here, that's Voyager 1. Okay, Voyager 1, it comes into the gravitational field of Saturn. Okay, it's not touching it. Okay, it gains energy from the Saturn and then it goes to Uranus. Okay, so we can say that there's no collision happening there. Okay, then we know the dinosaurs died due to collision of the asteroid with Earth. Okay, that you must know that. So these are some of the examples. Let me erase this thing here. Okay, that's to show that collision can happen without physical contact also. Asteroid impact is a collision which happens if two things hit each other. Okay, the asteroid will go hit the Earth. That's one thing we know. Then we say in a car crash. Okay, a car may go to another car and crash. So that's the kind of collision. Okay, that's an example. So you can take any kind of collision. The linear momentum is conserved in all collision process. Okay, so you can see that the linear momentum is conserved in all collision process. Okay, so we'll see what's the meaning of this. This momentum is conserved. Okay, momentum means product of mass and velocity. That's conserved in all collision process. Let me see that now. Okay, I'll erase this board. We'll see with an example. Okay, now let's see how linear momentum is conserved during collision. Okay, let's study it now. Okay, we'll take an example here. For example, a striker goes hits a coin. Okay, in the game of carom. Okay, so this striker here. The striker, let's name it as 1, and the coin we name it as 2. Okay, so this happens before collision. Okay, imagine the coin is also moving. Okay, this happens before collision. Okay, like this way, the striker and coin go to the right side. Next, what happens is during collision, what happens? The striker will hit the coin. Okay, the striker goes and hits the coin here. This is the first one. This is the second one. The striker and coin hit each other. Okay, this happens during collision. Let me write it down. During collision. So let's see what happens during collision. The striker, the first object, will give a force on the second one. So force is given on the object 2 by the object 1. Okay, force on 2 by 1. Then the object 2 also will give a force again in the reverse way. That is Newton's third law. Okay, there's a reaction force. That will be force on 1 by 2. Okay, force on 1 by 2. This happens during collision. There's equal and opposite forces there, action force and reaction force. Next, we'll see what happens after collision. Okay. The first object goes this side, the second object also goes this side. Okay, this happens after collision. Now we have to prove that the linear momentum is conserved. Okay, let me take another chalk here. So linear momentum is conserved, that you may see. First we'll see the change in momentum. Okay, what's the change in momentum? We know the formula for force. According to Newton's second law, force is equal to the rate of change of momentum. Okay, that is written in this form, delta P by delta T. So if cross multiply this delta T upwards, we get here F into delta T is equal to delta P. That means the change in the momentum. Okay, so let's see this now. What's the change in momentum? Okay, the change in the momentum. Okay, momenta we'll see. Okay, actually plural we have to use here. The first object and second object. What happens to the change in momentum? Okay, so we'll see change in momentum of the first object, that is delta P1. Okay, momentum is vector, so write as vector symbol. Okay, that's equal to this formula here, F into delta T. So we write here force into delta T. Okay, but what happens to the force on one? That force we write as F12. Okay, F12 into delta T. Again force the vector, so write as vector symbol. Next, what you will see, what's the change in momentum of the second object? That is delta P2 is equal to, similarly, the force here. Force on the object 2 by 1. So F21. So force on object 2 by 1, F21 into delta T here. Okay, let's name this as equation 1 and this is equation 2. Okay, now what we do is we have to add these two momentum. Okay, this is momentum, this momentum first object and momentum second object we must add. So add equations 1 and 2. Add the equations 1 and 2. So when you add it, what we get is delta P1 vector plus delta P2 vector. Okay, this momentum vector, that's equal to this one, F12 into delta T vector symbol again plus F21 into delta T. Okay, now you can see here what's common here, delta T is common. Okay, so let me take delta T outside. So we get here F12 plus F21 into delta T here. Okay, this we have here. So according to Newton's third law, we know that this force and this force are equal and opposite. Okay, F12 is equal to F21. Okay, so according to Newton's third law, we see that F12 is equal to, it's equal and opposite. So in physics, what you write is you write a minus sign to show the opposite sign, minus of F21 vector. Okay, so if you see that F12 is equal to minus of F21, so you have a minus term. Okay, these two terms will cancel each other. So you can say that the momentum, change in momentum comes to be 0. Okay, or you can say that delta P1 vector plus delta P2 vector is equal to 0. Okay, let this be here. Now I'll erase the board from this side. Okay, leave the last equation and I erase up to here. Okay, now what we do is we have divide both the sides by delta T. Okay, the change in time. So divide both sides by delta T. Okay, and then what we do, we take the limit and take limit of this delta T. That means the change in time tends to be 0. Okay, so now we'll take this equation and divide by delta T. Okay, you can see one more thing, delta is common here, so we can take delta outside. So delta into P1 plus P2, okay, divided by delta T is equal to 0. Be 0 by anything is 0 only. Okay, now what we do next step is we must take the limit of delta T tends to be 0. Okay, that we'll do it next. Let me erase it first. Okay, now this delta T tends to be 0, so we take the limits here. Limit of delta T tends to 0. Okay, that means we take a very small time. Okay, the time of collision is very, very small. So I'll take the equation, write down. So delta into P1 plus P2 vector divided by delta T is equal to 0. Okay, so when we take limit of this term to be 0, okay, we can write this as a differential form. Okay, differentiation format you can write here. Okay, that instead of this we can write as d by dt. Okay, d by dt, that means small change in time of momentum P1 plus P2, okay, is equal to 0. So what we understand from this? Okay, we know the formula for differentiation. Differentiation, okay, of a constant, that c is equal to 0. If you differentiate 5, it is 0. Okay, so 5 is a constant. Same way we can see that in this case p1 plus p2, that means sum of the momentum is a constant. That means we can say momentum does not change. Okay, momentum is a constant. So we can say that in this case here, what we understand from this is the total linear momentum, is a conserved quantity. Total linear momentum is a conserved quantity. Okay. So this is what you understand, because differentiation of constant only will give us 0. So we can say the momentum is a constant here. It is conserved. It doesn't change that. Okay. This is about the topic of collisions. In the next video we'll see what are the different types of collisions. Okay. Thank you for watching.